Okay, so welcome back to the digital image processing course, and this week we will be discussing on the domain transformations. Okay, so what is different now? So far what we have been doing is every operation was in the spatial domain, or most likely the domain at which the image was occurred. Okay, so we discussed about point level operations in terms of intensity as well as geometrical operations. We also discussed about spatial operations where we consider the neighborhood into the uh, operation, right? We discussed about filtering, for example, linear and non-linear filtering, and lot other things which are actually still in the same domain as the spatial domain. Okay. Now we are talking about considering a different domain representation for the image and what is the use case and why it is so important and all those aspects, okay, in this week and maybe in the next week as well. Okay, so I would like to start with an interesting application. Okay, so this is an image of two children playing, and we can see that this image is really corrupted by some sort of a periodic noise. And if you go back to something like lecture 1, maybe hands-on session of lecture 1, you could see that you have created such periodic patterns, right? You might have to just dig and see whether you can recall this. Okay, so now our objective is to remove this periodic noise. So I'm sure there's some noise running. I want to remove this noise. Such noise, which is actually this sort of disturbance, is commonly known as Moire pattern. Okay, so this is very interesting. Okay, this can be observed if suppose you would record your monitor, okay, for example, or a TV using your mobile phone camera. If you do that, you can immediately see that these sort of patterns are running. Okay, so they are known as Moire's patterns. The reason why such patterns exist is because there is a slight mismatch in the case of camera and TV screen, a slight mismatch in the refreshing rate. Okay, the rate at which the screen is refreshed is slightly different compared to that of the camera speed. Okay, so if that happens, you will have this sort of pattern, which is typically known as this Moire's pattern. Okay, so how shall I go about removing this? So whatever we studied so far, if we apply smoothing on this, a smooth filter, low pass filter on this, some improvement definitely can be expected. But the problem is this pattern will also get smooth and it won't go really, right? The next option is you could try the nonlinear filter like median filter. But then the problem with median filter is like it applies very well if there are spurious peaks, spurious values. But if there is consistent periodic pattern like this, it's really not going to help. So what shall I do? Okay, so that's the thing you should be asking by now. Okay, so I'm going to do a clever trick here. So I'm going to represent this image in a different domain where this noise can be nicely captured. Okay, so the problem with this noise in this spatial domain, it is throughout present, right? In the spatial domain, it's really difficult to decouple the noise from the image. So if I can represent the image in a different domain, okay, in this specific case, because it is periodic and it looks like a sinusoidal periodic pattern, I can represent this noise concisely in a Fourier transform. Okay, so that's what we are going to do. So I'm going to transform this image by taking the Fourier transform of this image into the frequency domain representation, or some people call it as Fourier domain representation, and it looks like this. Okay, so when I take Fourier transform, so you may not be knowing Fourier transform, what is it? Those coming from signal processing background definitely knows it, but if you're not knowing it, forget about it. We will discuss it in the next slide. Okay, so don't worry about it. So some transform, okay, some operation which I do on this image will give me this, and this operation is nothing but the Fourier transform. Okay, and if you see over here, I'm able to see so many localizations. Okay, and let's assume that this square, which is the outermost square, the bright line square that I'm seeing, is this periodic pattern. Okay, so then all I need to do is just remove that. Okay, so for that purpose, I'm going to multiply this image by a image which is looking like this, which means white all throughout and only dark in these regions which are coinciding with these white lines. Okay, so my objective is to remove these lines, that's all. So all other regions are untouched except this pattern will be gone. So if I multiply these two, I'll get something like this. So the difference between this image to this image is nothing but these bright lines, these white lines, the outer square is completely gone. Okay, now I need to go back to the original domain. So I went to Fourier domain, I did some operation, now I need to go back to the original domain. So how shall I go about? I shall take the inverse Fourier transform. So if I take the inverse Fourier transform, I end up getting, wow, a very good image which is sort of cleaner compared to this. Okay. So if you do directly any spatial filtering operation, you will never be able to achieve this sort of a result. Okay. So what we did actually is very interesting. Okay. So it is something like this. So you have the image space, right? So and then you went to a domain representation of the image. So in this case it is Fourier transform, and then in the domain you do some processing. Okay. And then from there you went back to the image space. So I'll say it as modified image, right? So this is something we call as forward transform, and this is basically the inverse transform. That's exactly we did in this case, right? And it is really difficult to do, achieve the similar result if I directly go from here to here by some process. It's almost impossible. Okay, so that's what the beauty about domain transform is. So I hope I'm nicely introduced and it's pretty clear what is the motivation of representing an image in a different domain. Okay, the whole motivation is that some information can be concisely represented in the different domain compared to the spatial domain, exactly like this. Okay, and you can immediately see that one of the beautiful applications of domain representation is definitely going to be compression. Okay, so we will discuss that at some point. So I will be able to represent my image in a nice concise fashion in another domain where most of the things will be sparse or will not be having any value, just like this. Okay, so most of them is dark except few bright spots that you're seeing. Okay, so it's concise representation of the image. Okay, so let's move on and define one of the most standard transforms, 2D transforms, which is the Fourier transform. Okay, so but before going to that, I would like to have a generic representation or generic mathematical equation representing the domain transform. Okay, so in this case the domain transform is f of uv. Okay, u is actually, you can take any value just like x and y. So u and v are the coordinates. Okay, so I would like to put this way, coordinates of your domain. Okay, representation. Okay, so these are uv are the coordinates, so it can take some values as defined by you. You define the mesh grid size, okay, for u and v, and so basically this equation has to be repeated for each u and v. Okay, so remember that. Okay, and now let's see the right hand side. Okay, so what is f of xy? F of xy is your original image which runs through all the pixels. That's what happening here, right? X and y. So every value, or basically this is an image. Okay, f of xy is nothing but the image. And what is phi of xy? Okay, so phi of xy is your transform function, the forward transform, for example. Okay, so once you fix a u and v, the phi of uv becomes a scalar in terms of u and v, but it is still a matrix in terms of x and y. So what essentially you are doing over here is f is dot product with phi. Okay, so this is what actually happening in this entire expression. So in terms of if you're really keen in what is happening exactly, each pixel is multiplied. Okay, so each pixel of f and phi are multiplied, and what you're doing is you sum it over all the pixels, and that single value, one value, will be kept at the coordinate location uv, and you repeat for other u and v, then your phi of xy will change, and then of course you repeat the same process and you create the domain representation of the image. Okay, so now let me just discard all this. Okay, so now let's officially define what is Fourier transform then. So this is generic representation. Now let's go to the specific representation of Fourier transform. If you see, the formula remains same. The only change is you going to define what is your forward transform function is, and this is sorry for that. Okay, so let me draw it nicely. So this is your basically the forward transform function, and that is nothing but a sinusoidal function which is represented by this. Okay, and now it is very important to note that this is something like you can treat it as a matrix multiplication. We will see that in a few slides from now. Okay, so how to go about it. So what you are going to do is you are basically doing a dot product of your image with some function, and some people call this function, maybe computer science people will better appreciate that terminology. This function is something known as the basis function. Okay, so you can define any basis function and we will study that. So in the case of a Fourier transform, the basis function is a sinusoid. Okay, sinusoid is nothing but a combination of a cosine and a sine function. Okay, so we will come to that in a brief. So this basis function can be anything. It can be a different function like a Haar wavelet, a square function. Okay, so then it becomes a wavelet transform. It can be something like a Hadamard transform. It can be something like different varieties of waveforms you can imagine as the basis, just like the sinusoid I am representing here. Okay, so now coming back to Fourier transform, this can be represented as something like e raised to minus j theta, where theta is this function which is inside. Okay, and that can be represented as a real and imaginary terminology according to the Euler's formula. Okay, so this is cos theta plus j sin theta. So it's a combination of cosines and sines. Okay, and that is why it is known as sinusoid. Okay, and what it essentially means is, okay, as if you go back to the first lecture, as I said, you are going to basically have a dot product or a similarity measure between your image and various frequencies. Okay, so that's what essentially happens. Okay, so it's interesting. I'll have a very interesting slide in the next one which clearly explains this in terms of a pictorial representation. So all you need to understand is, to have the Fourier transform, what you need to do is you multiply or you take a dot product of your image with all different possibilities or all different frequency combinations. Okay, and each one of them represents the Fourier coefficient. Okay, so let's put some value. Okay, so u equal to 0, v equal to 0. That means this will become 0, this will become 0. That is e raised to minus 0, or e raised to 0 rather, is nothing but 1. So this term will vanish for that, and then it just becomes what? If u equal to v equal to 0, what it essentially is just the summation of all the intensities of all pixels. So it's something like average value. Okay, electrical engineers call it as DC value. Okay, so that's exactly what it means. So the first particular basis function is nothing but a DC value or an average value. Okay, so that's it. And then you have the next frequency, so that means u equal to 0 and v equal to 1, for example. So then some frequency will be generated, that will be an image. Okay, because you have to vary x and y, so x and y will vary in rows and columns, so it becomes an image. Then you do a dot product of the image f of xy with that particular image, sum it up and put that value in f of u comma v. Okay, so that's how you generate the entire thing. So that is a forward transform. Now what about reverse or the inverse transform? So forward transform is nothing but you want to convert f of xy to f of uv. You want to represent your image in the Fourier domain. Okay, so this is the Fourier domain representation. And inverse transform is to convert the Fourier domain representation back to your spatial domain. Okay, and see the difference. There is no difference at all. The only difference is just this. Okay, only the difference is this is minus and this is plus, and that's the beauty. Okay, so inverse transform and Fourier transform, inverse and forward Fourier transforms are related by just a conjugate, right? I mean, it's sort of a complex conjugate of your basis function. Okay, so now let's move on. Okay, so now I am going to pictorially represent this. Okay, so what I said here is u and v are going to change. Okay, so u equal to v equal to 0 is nothing but the average value of the DC component. So it's the same value throughout. Okay, so what I'm going to show you in the next slide is what the pictorial representation of this particular function. Let me just discard the ink. Okay, so pictorial representation of this particular function for various values of u and v, assuming x and y is some 2D space. Okay, so that's what we are going to see. Okay, let's go there. Okay, so if you see over here, this is what u equal to v equal to 0, and you can see over here it's just a constant value, right? Because e raised to 0 is 1 and you just have sum of your image. Okay, but this what I'm going to show is just the basis function. Okay, just that e raised to minus j term for different u's and v's. So in this case I'm taking u equal to minus 2 to u equal to 2, and similarly v equal to minus 2 to v equal to 2. Okay, so what essentially, let's concentrate on this part because essentially all others are sort of replication. Okay, so let's concentrate on this region. Okay, so this is the 0 0 region, the central region. As I go along the horizontal axis, what essentially is happening is there is an increase in frequency. This is roughly a positive and a negative, so one cycle. This is actually positive, negative, so two cycles, and so on. Okay, so there is an increasing frequency trend. Again, go back to the lecture we had, right? We in fact nicely generated these images. Okay, and if you go down, it is just the opposite. So here it was horizontal sine wave, here it is vertical sine wave, and if you go diagonal, it is basically diagonal. It's combination of these two sinusoids, sort of a diagonal sinusoid, right, in going in one direction. Okay, so let me just erase it. So if you see in this direction, this guy and this guy are exactly same, this guy and this guy are exactly same. Okay, and similarly this guy and this guy are exactly same, and similarly here this guy and this guy are exactly same. So this is a symmetricity for the Fourier transform, and it is sort of even symmetric, right? You have a center and across that it is symmetric. Okay, so it's very important to notice. So what is then Fourier transform? Okay, so let's now explain that using this particular basis function representation. So all these are bases actually. So this is the first basis when u equal to 0 and v equal to 0. Please always remember this is obtained from this. You put u equal to 0, v equal to 0 and vary the x and y in terms of an image, you get this particular nice representation. Similarly, u equal to 1, v equal to 0 will be represented by this image. U equal to 2, v equal to 0 is represented by this image, and so on. So Fourier transform, what it essentially does is you do a dot product between your image and each of these small images. Okay, so each of these small images will be having a dot product with the image, and whatever value is coming, you will be replacing this particular location. Okay, and then this particular location, and then this particular location. Then I view it together, I get an image which is something very similar to what we saw in this case. Okay, so this is basically the Fourier transform where I evaluated for all u and v's. Okay, and finally when I stitch them together and have an image, I get an image similar to that. Okay, so essentially all these will have an image form like this depending on the value of u and v. Okay, and now as I said, it's sort of symmetric. So what essentially you do is, I mean, you can only consider this region, and that's what actually represented here. So v in the negative side and u in the positive side. So u in the positive side and v in the negative side. So what essentially, again, I just want to highlight this part again, sorry. Okay, so this is the DC value. Okay, this is the DC value, and this in terms of increasing frequency, again, this is more of in the x direction, this is more in the y direction, and this is more in the diagonal direction. You can see that it is just increasing frequency. Okay, so what essentially you have will be the coefficients, the similarity measure, the correlation value between this particular image and the original image. That particular value, whatever is the correlation value, basically going back to the formula here. Okay, so basically you always remember this. Okay, you do sort of dot product, and finally you will have one value for that pixel. So basically when u equal to v equal to 0, you will have one value which is representation of the entire Fourier coefficient. Okay, so the entire similarity of the image with the u equal to v equal to 0 will be here, and similarly this one, this one, this one, and you create the entire image. Okay, so that is how the Fourier transform works. Okay, I hope it's very, very clear for you. Okay, now let's actually see how in a MATLAB, for example, or in a Python, for example, how can you calculate the Fourier transform. Of course, you have commands like FFT2 which will give you the Fourier transform directly, but you can actually put it as a matrix operation also. It's as simple as this. So this is original Fourier transform definition again. So one of the things you can always do is this is actually separable in terms of, you can assume this to be something like two 1D transforms. Okay, one along row direction, the other one along column direction, something like this. So between these two there is only one change. I just put the one dimension together. So this can be represented as e raised to minus j 2 pi ux by m into e raised to minus j 2 pi vy by n. So once I do that, I can decouple. So this is one dimension. Once this result is done, you do Fourier transform of this result with the other dimension. So first you may do row, and then you may do column, and this can be represented as a nice compact matrix representation. So W is nothing but your Fourier transform matrix or the basis function matrix. You can see over here this u value is varied, so u equal to 0, 1, 2 and up to n minus 1, and this n is basically nothing but your x vector or the y vector, okay, up to you. So this is nothing but the w, okay. So you do w into f, you are basically doing this operation, okay, and then if you do w transpose, you will do the y operation. So this is the sort of a crisp and very good notation of a matrix representation, matrix operation representation of Fourier transform, okay. So this is very generic, and any transform that you are going to see later on can be represented in this sort of a matrix multiplication formula, okay. So I hope it's very clear, and we can try out some examples later on, okay. So, and yeah, this is something which is very important. So if I so let's do, okay, w is basically the Fourier forward transform, and if you see w transpose, okay, so w transpose, or in this case always remember w is a complex matrix. It has a real and imaginary part, the cosine and the sine part, okay, and the result also is going to be complex, okay. The Fourier transform is always going to be complex. So what you're seeing over here, okay, maybe I just need to go back and explain that. It's a nice time to go back and see this chart, okay. So what you're seeing over here is the magnitude of the Fourier transform. So once you take Fourier transform, you will have a cosine component and you will have a sine component, and you basically do a square root of your real and imaginary part, real square plus imaginary square root of that. That's the magnitude of the Fourier transform, okay, and in that sense you will have the phase also. So we will see that, okay, later. Okay, so I hope this is very clear. So if I do sort of multiplication between them, you get sort of unitary matrix, basically identity matrix, okay, and then some scalar, okay, and such transforms, if you can represent any transform, the forward and reverse like this, such transform is commonly referred to as unitary transformation. So okay, unitary as the name suggests, resulting in an identity matrix or one value, okay. So this is just for your understanding. There's nothing really major thing about it, but just for your better understanding, it's important to note this. There are certain advantages for unitary transformations, okay, because they are easily invertible, okay. So I would like to stop this particular lecture by just showing you a very important example, okay. So you have the Bay image, okay, and its Fourier transformation, which is represented here, okay. And one thing I did over here is actually this center of the Fourier transform is the 0 0, okay, u equal to 0, v equal to 0 lies at the center, okay. So the Fourier transform of this image is shown over here. Basically this is a magnitude of the Fourier transform, okay. Let me put it that way because it should be very clear, okay. And similarly this moon image, if you see, this is the magnitude of the Fourier transform of this moon image, okay. Now I have a question here, okay. If you compare the Fourier transform this image and this image, basically this Bay image and the moon image, there is an important striking factor, which is a horizontal line. If you see, sorry, a vertical line which is going along, which is very sort of visible here, and even some diagonal line also can be seen, okay, which is really not visible here except for this dark image that you're seeing over here, okay. And why this white line is coming, this is very important, okay. And this actually is because of an underlying assumption of Fourier transform, okay. So when I take Fourier transform of an image, okay, there is a fundamental mathematical assumption which is going to happen, okay. The assumption is that this image is actually, so let's think this way. So what is this image? This image is bounded by this particular window, right? What is outside of this image? That is really an unknown entity to us, right? So Fourier transform has an official definition that it assumes that the image is sort of continuous outside, in the sense like the image gets replicated outside, okay. So this is something like this, okay. So when you take Fourier transform, the assumption for Fourier transform, or the biggest assumption for Fourier transform is like that this image is, or this image basically is a part of a bigger image which is something like this, the same image which is replicated in all along diagonal as well as east west and north south directions, okay. So you see this is our original image, but my assumption is that the image is actually everywhere, okay. So it is something which is a very fundamental assumption of Fourier transform, applicable to 1D also. Those who studied signal processing can easily think in that perspective. Okay, so when you take a 1D signal, the Fourier transform of that signal, your assumption is that the signal is periodic outside. Okay, so before that and after that the signal remains same, so it is the periodic repetition of the signal is a fundamental assumption behind the Fourier transform. But in the case of an image, it is simply image getting replicated everywhere in all possible neighborhood. Okay, so that's what happens. Now if you see, there is an issue, right? If you see here, just see the Fourier transform at the edges of the image. In this case, for example, you see there is a dark shade here and a bright shade here, so it appears like there is a sudden transition, and any sudden transition in an image will look like an edge, right, for an image. So there is a very high sudden transition, particularly in this direction, particularly in the what you call the raw direction. Okay, so the what direction is this for us? This is the y direction. Okay, so what essentially happens is, in terms of a signal processing engineer or a control systems engineer, there is a sudden jump, there is a sudden change in intensity, and any sudden jump, any sudden change in intensity, we call it as impulse, right? There is an impulse, there is a sudden change, or there is a step change. Okay, so then what happens is, basically such a change will excite all the frequencies in that direction. Okay, and that is precisely what is happening here. Okay, so in this case there is a sudden jump in the horizontal direction, or the, sorry, this is the vertical direction, in the y direction, and that is what actually happening as a bright line here. So that means all the frequencies are going high in this particular direction. Okay, so but if you see along the rho direction, along the x direction, the change is not really sudden. There is a gradual change compared to this. That may be the reason why you are not really seeing any horizontal line, okay, going here. Only you are seeing the vertical line. And now coming back to this, okay, this is very interesting. Okay, so the what will be this image looking like for a Fourier transform? Exact replica of this. But then there is an advantage here. You see the border, it is all dark. Okay, so if I replicate this image, the interface will also be looking like a dark continuous region, right? Not like this jump. It will be all dark. If you think of replicating this image like this, so then what essentially happens is, the same image will come here, but then there is a dark to dark region, here also dark to dark, here also dark to dark, here also dark to dark, even diagonal also is dark to dark. That means there is no sudden change, and that is why there is no white lines like in this image. So this image clearly has a white line. The Fourier transform of the Bay image has clearly a white line. The reason is because there is a sudden transition. In the case of this image, there is no sudden transition like this. Okay, so this is a fundamental assumption, very, very important hypothesis which is assumed in Fourier transform, and please do remember that all the time, because moment you see a vertical line or a horizontal line in the Fourier transform, it means that there is an edge. Okay, there is an artifact, and how to go about avoiding it? The only possible is, like, instead of assuming it to be like this, you multiply the image with a Gaussian window. Let's say you have a Gaussian window with center at the mean of the Gaussian at the center of the image, and then the spread almost covering the entire image. So in that way you can actually sort of reduce the intensity values at the border, and if you do that, you will have something similar to this image, right? Then you have some sort of continuity at these regions, and then that will remove all these artifacts, okay, all these edges. So always remember these such small nitty-gritties that people don't really have express in the textbook or in the standard lectures, but I would like to highlight it here. This always happens, and you will be wondering where it is coming from, and the reason for this is the fundamental assumption behind Fourier transform. Okay, so this is really interesting, right? And with that we will stop the quick introduction to the Fourier transform, and we will deep dive into a lot of interesting aspects about Fourier transform in the subsequent slides. Okay, so till we see in the next lecture, bye from my side, and see you all in the next lecture. Thank you.